Assalamualaikum, my dear friends. How are you? I hope you are best. Welcome to my channel. My topic today about which I give you information about what is iron. I will completely teach you about iron. But first of all, if you are new, so also please subscribe my channel and press the bell icon. So I have start my topic about iron. And inshallah ta'ala, his video very technical and very formal. Inshallah ta'ala, and very much information you take in this my topic. So now I have start about iron information. And if you are new, so also please subscribe my channel, press the bell icon. So you start my topic about iron. Iron is a chemical element. It has a symbol Fe from Latin ferrum iron, and atomic number is 26, and it is a metal that belongs to the first transition series and group 8 of the periodic table. It is by mass the most common element on earth, forming much of Earth's outer and inner core. It is the fourth most abundant element in the earth crust, being mainly deposited by meteorites in its metallic state. Extracting usable metal from iron ores requires kilns or furnaces capable of reaching 1500 degrees C and 2730 degree F. About 500 degrees C and 932 degree F. Higher than that required to smelt copper. Humans started to master that processes in Eurasia during the second millennium BC, and the use of iron tools and weapons began to displace copper alloys in some regions. Only around 1200 BC, the event considered the transition from the Bronze Age to the Iron Age. In the modern world, iron alloys such as steel, stainless steel, cast iron, and special steels are by far the most common industrial metals due to their mechanical properties and low cost. The iron and steel industry is thus very important economically, and iron is the cheapest metal with a price of few dollars per kilogram or pound. Pristine and smooth pure iron surfaces are a mirror-like silvery green. Iron reacts repeatedly with oxygen and water to produce brown to black hydrated iron oxides, commonly known as rust. Unlike the oxides of some other metals that form pervading layers, rust occupies more volume than the metal and thus flags of exposing more fresh surfaces for corrosion. Chemically, the most common oxidation states of iron are iron 2 and iron 3. Iron shares many properties of other transition metals, including the other group 8 elements, ruthenium and osmium. Iron forms compounds in a wide range of oxidation states, -4 and to +7. Iron also forms many coordination compounds, some of them such as ferroquine, phosphorylate, and Prussian blue have substantial industrial, medical or research applications. The body of an adult human contains about 4 grams, 0.005 degree body weight of iron, mostly in hemoglobin and myoglobin. These two proteins play essential roles in oxygen transport by blood and oxygen storage in muscle to maintain the necessary levels, and human iron metabolism requires a minimum of iron in the diet. Iron is also the metal at the active site of many important redox enzymes dealing with the cellular respiration and oxidation and reduction in plants and animals. And allotropes of iron. At least 4 allotropes of iron, different atoms arrangements in the solid, are known. Conventionally denoted as A, Y, O, and E. The first 3 forms are observed at ordinary pressure. As molten iron cools past its freezing point of 1538 degrees C, it crystallizes into its zero allotrope, which has a body centered cubic BCC crystal structure. As it goes further to 1394 degrees C, it changes to its Y iron allotrope of phase centroid cubic FCC crystal structure or actinide at 912 degrees C, and below the crystal structure again becomes the BCC a iron allotrope. The physical properties of iron at very high pressures and temperature have also been studied extensively because of their relevance to theories about the cores of the Earth and other planets. Above approximately 10 GPa and temperature of a few hundred Kelvin or less, iron changes into another hexagonal close-packed SCP structure, which is also known as E-iron. The higher temperature Y phase also changes into E-iron, but does so at higher pressure. Some controversial experimental evidence exists for a stable B phase at pressures above 50 GPa and temperature of at least 1500 K. It is thought to have an orthobic or a double SCP structure. Confusingly, the term B iron, beta iron is sometimes is also used to refer to a iron above its Curie point when it changes from being ferromagnetic to paramagnetic even through its crystal. Even through its crystal structure has not changed. The inner core of the Earth is generally presumed or consists of an iron nickel alloy with E or beta structure. Melting and boiling points of iron. The melting and boiling points of iron, along with its enthalpy of atomization, are lower than those of the earlier 3D elements from scandium or to chromium, showing the lessened contribution of the 3D electrons or to metallic bonding as they are attracted more and more into the inert core by the nucleus. However, they are higher than the values of the previous element, manganese, because that element has a half-filled 3D subshell and consequently its Da electrons are not easily derived. The same trend appears to ruthenium but not osmium. The melting point of iron is experimentally well defined for pressure less than 50 ppm. For greater pressure, published data as of 2007 still varies by tens of gigapascals and over 1000 Kelvin. And its magnetic properties below its Curie point of 770 degrees C and 1420 degrees F and 1040 K. Iron change from paramagnetic to ferromagnetic. The spins of the two unpaired electrons in each atom generally aligned with the spins of its neighbors, creating an overall magnetic field. This happens because the orbitals of those two electrons are dz square and dx square, negative y square. Do not point toward neighboring atoms in the lattice and therefore are not involved in metallic bonding. In the absence of an external source of magnetic field, the atoms get spontaneously partitioned into atomic domains about 10 micrometer across, such that the atoms in each domain have parallel spins, but some domains have other organizations. Thus, a macroscopic piece of iron will have a nearly zero overall magnetic field. Application of an external magnetic field causes the domains that are magnetized in the same general direction to grow at the expense of adjacent ones that point in other directions, reinforcing the external field. The effect is exploited in devices that need to channel magnetic field to fulfill design functions, such as electrical transformers, magnetic recording heads, and electric motors. impurities. Latente fracts or gain and particle boundaries on pin that remains in the new position so that the effect persists even after the external field is removed, thus turning the iron object into a permanent magnet. And similar behavior is exhibited by some iron compounds such as ferrites, including the mineral magnetic or crystalline from a mixed iron 2 and 3, oxide Fe3 and O4. And pieces of magnetic with natural permanent magnetization provided the earliest compasses for navigation. Particles of magnetite were extensively used in magnetic recording media such as core memories, magnetic tapes, floppies, and disks until they are replaced by cobalt-based materials and its isotopes of iron. Iron has four stable isotopes: Fe54, 56, Fe56, Fe57, and 58, and 24 artificial isotopes have also been created. Of this stable isotope, only 57 Fe has a nuclear spin negative 1 by 2. The nuclide 54 Fe theoretically can undergo double electron capture to 54 Cr, but the process has never been observed and only a lower limit on the half-life of 4.4 multiplied 10 20 years has been established. Fe60 is an extinct radionuclide of long half 2.6 million years. It is not found on Earth, but its ultimate decay product is its granddaughter, the stable nuclide Ni. Much of the past work on isotopic composition of iron has focused on the nucleosynthesis Fe60 through studies of meteorites and earth formation. In the last decade, advances in mass spectrometry have allowed in detection and quantification of minor naturally occurring variations in the ratios of the stable isotopes of iron. Much of this work is driven by the earth and planetary science communities, although applications to biological and industrial systems are emerging. And in phases of the meteorites, Americana and Chervony cut correlation between the concentration of 60 Ni, the granddaughter of Fe60, and the abundance of the stable iron isotope provided evidence for the existence of Fe60 at the time of formation of the solar system, and possibly the energy released by the decay of Fe60 along with that released by Al26 contributed to the demelting and differentiation of asteroids after their formation 4.6 billion years ago. The abundance of 60 Ni present in extraterrestrial material may bring further insight into the origin and early history of the solar system. And the most abundant iron isotope Fe56 is of particular interest to nuclear scientists because it represents the most common endpoint of nucleosynthesis since 56 Ni. 14 alpha particles is easily produced from lighter nuclei. Is the alpha process